Hello all, I am Dr. M. Laxmidevi, Associate Professor in the Department of Electrical and Electronics Engineering at Institute of Aeronautical Engineering. Welcome to the course Electrical Measurements and Instrumentation. Today's topic is PMMC instruments. So before discussing about PMMC instruments, let us see what is a voltmeter and what is an ammeter. So voltmeter is the instrument which is used for measuring the voltage across the circuit, whereas voltmeter and ammeter. So this is an ammeter as seen in this diagram, and this is a voltmeter, a practical ammeter and a practical voltmeter which is used in laboratories. So voltmeter is connected in parallel with the circuit whose voltage is to be measured, and ammeter is connected in series with the circuit where current is to be measured. So the requirements of voltmeter and ammeter are, we have the formula P loss is equal to I square into R. This is for an ammeter, and for voltmeter V square by Rm. This is for a voltmeter. So from this we can say that for the voltmeter to be used in the circuit, the resistance which is used in parallel with the voltmeter should be as high as possible so that the power loss will be less. And for the ammeter, the resistance in series with the ammeter must be as low as possible. Here it should be as low as possible so that the power loss is reduced. For the power loss to be reduced, the series resistance must be as low as possible. So in ammeter, ammeter is to be connected in series with the, so here ammeter is connected in series with the circuit. Ammeter is connected in series with the circuit, whereas voltmeter is connected across the circuit where voltage needs to be measured. So here this is the voltmeter. If we want to measure the voltage across this resistance R, then we need to connect this voltmeter across this element. If we need to measure the current in this circuit, we need to connect the ammeter in series with this circuit as shown here. So the important requirements of any instrument are, so it can be a voltmeter and ammeter. So the basic fundamental or their operating principles of voltmeter and ammeter are same. So we can group them into the same category. There are some important characteristics for an instrument to be used for measuring purpose. So they are, first one should be characteristics of an instrument to be used. Used for measuring purpose are, first of all, it should not alter the circuit conditions or circuit parameters. It should not change the instrument when used for measuring purpose. It should not change the circuit conditions. And the second one is the power absorbed the power consumed by the meter or instrument, it should be less. So these are some of the important characteristics of an instrument. So we are talking about, in this class we will discuss about analog voltmeters and ammeters. So analog voltmeters and ammeters, they depend upon input is electrical and output is mechanical. There is output is mechanical movement of the pointer. So here the mechanical movement of the pointer in case of ammeter is due to the deflecting torque, as we have seen. So this deflecting torque in ammeter is proportional to the current which is to be measured, and in case of voltmeter, this deflecting torque is proportional to the voltage which is to be measured, and that voltage is in turn proportional to the current. Now let us see the different types of instruments which can be used as voltmeters and ammeters for measuring voltage and current. So the first one is among them is permanent magnet moving coil instrument. So it is abbreviated as PMMC instrument. The next one is moving iron instrument. So abbreviation is MI instrument. We also refer it as MI instrument. Next one is electrodynamometer type instrument. So EMMC instrument. Next one is electrostatic type. So ES. Next one is electrothermic instrument. So these permanent magnet moving coil instruments, they can be used only for measuring DC quantities. So that is what written here. Next, coming to moving iron instruments, so they can be used for measuring both AC and DC quantities. Whereas electrodynamometer type instruments, so even they can be used for measuring both AC as well as DC quantities. Electrostatic type can be used for AC and DC quantities. Electrothermic type also can be used for measuring AC and DC quantities. So in this class, we'll discuss about the working, construction, then errors, and then some of the advantages and disadvantages of permanent magnet moving coil instruments. So apart from that, we'll also see how to extend the range of this instrument when it is to be used as an ammeter and when it is to be used as a voltmeter. So coming to the working principle of PMMC instruments, so we can see here in this diagram. So let us understand this diagram and then we will see the working principle of PMMC instruments. So we have two magnets here. So we can see here these are the two permanent magnets. Now consider permanent magnets. So let this be North Pole and this be South Pole. Consider a rectangular coil is placed in between the two magnets, in between the two poles, North Pole and South Pole. Current the direction. Consider the direction of the current in this side of the coil as I, and here this is the direction of the current flowing in the coil. So according to we have that when a current carrying conductor is placed in a magnetic field, the conductor will experience a force. So according to this law or this statement, we can say that, so this is the current carrying conductor and it is placed in the magnetic field which is produced by these permanent magnets. So because of this, the conductor will experience a force and it will try to rotate. So there are forces acting on the conductor on this side as well as on this side of the coil. Now let us understand this. So the direction of the force is given by Fleming's left hand rule. Fleming's left hand rule. So consider this as the conductor or this side of the coil which is carrying current. So it is represented by dot here. Dot means this is the current direction is towards us, whereas here it is represented by cross, whereas in this side of the coil has current flowing away from us. So this is what we represented. This direction, and the direction of the magnetic field will be anti-clockwise in this conductor, whereas it will be clockwise in this conductor, as you can see here. So this is clockwise and this one is anti-clockwise. Next, we know that this is the North Pole and this one is the South Pole. So flux lines will flow from North Pole to South Pole. This actually it should be in this way, but because of this magnetic field, you can see that the field lines are distorted. So field lines are distorted. So they are concentric at one end and they are spreaded at the other end. So at this side you can, and these flux lines, they will travel along the least reluctance path from the North Pole to the South Pole. So we know that when a current carrying conductor is placed in magnetic field, the conductor will experience a force. So this is the current carrying conductor under the, and this is the magnetic field produced by the North Pole and South Pole. So here the conductor will experience a force. Direction of this force is given by Fleming's left hand rule. According to Fleming's left hand rule, so this is the rule we can see here. If the first and second finger and the thumb of the left hand are held such that they are at right angle to each other, then the thumb represents the direction of the force. So this is F on the conductor. The first finger, that is this finger, represents the direction of the magnetic field, and this is the direction of the current. So there is twisting force on this side of the coil as well as on this side of the coil, due to which the coil will rotate. Coil will rotate, so torque will be acting on the conductor or the coil, you can say here. So torque will be acting on the coil. So due to this torque acting on the coil will rotate, and since it is connected to the pointer, the pointer will also rotate and it will show the deflection on the scale. So this is the working principle of the Pmmc instruments. Let us understand in detail. So when a current carrying conductor is placed in a magnetic field, it experiences a force and tends to move in the direction as per Fleming's left hand rule. So you can see here, this is the arrangement. So these are permanent magnets arranged in the form of horseshoe magnets. So here in between we have the arrangement. This is the spindle which is carrying this springs, and attached to this we have a pointer. Then we have, so in between the two magnets we have aluminium former. Inside this we have a core also. So on the aluminium former there is a coil wound. This is 3D view and this is 2D diagram of Pmmc instrument. So here also you can see the same permanent magnets. Then zero control adjustment is there. So if the instrument is not showing zero, then with the help of this arrangement you can adjust it to zero. Then these are the pole shoes. Pole shoes, they are made up of soft iron. This is the coil. Coil is made up of copper. There are spiral springs. Spiral springs are used for providing controlling torque. Then soft iron core you have, on which we have aluminium, on which aluminium former and coil is wound. Then in between the magnets and the core there is air gap, and then counterweights is there, and these are the pole shoes. Now let us understand the construction of Pmmc instruments. So it consists of permanent magnets as it is shown in the diagram. So there is a moving system. Moving system consists of a spindle which is attached to a rectangular aluminium frame. A coil made up of thin copper wire is wound over the frame. The current which is to be measured is passed through this coil. There is a soft iron core placed in the space within the aluminium frame. There are two spiral springs mounted on the spindle to produce controlling torque. Pointer is mounted on the spindle. Mirror is placed below the scale to avoid parallax error. The spindle is supported by jeweled bearings. So we have permanent magnets as we have seen. So this is another view of Pmmc instrument. These are, as we know, there are two springs used. These are the spiral springs made up of phosphor bronze. They serve as for two purposes. So phosphor bronze to reduce the effect of temperature as well as to reduce the effect of aging. Two spiral hair springs are used. So these springs are used for leading the current in and out of the circuit, and also they serve as they provide controlling torque. The next one is soft iron core. As you can see, this soft iron core, it provides radial magnetic field so that force acting on the conductor is same at every point. So another function of soft iron core is, so it provides low reluctance path for the air gap between the poles. So this is the function of soft iron core. So next we have aluminium former. So aluminium former, it provides damping torque, and other function of aluminium former is it supports the coil. So these are the two functions of aluminium former. Next we have pole shoes. So the function of this is it provides radial magnetic field So you can see the another view of permanent magnet moving coil instrument. This is the uh, upper view, and this is another view of PMMC instrument. You can see here the same. So here we have control springs also. Control springs. So they are used for, it leads the current in and out of the coil with the help of control springs, as you can see here. So these are the springs. So here springs are connected to the so these are the leads into which. So on this we have the coil which is placed here. So this coil is connected here. So current is lead into the spring with the help of into the coil with the help of the springs. So this spring is attached to the and this is attached to this spindle on which the spring is there. Here we have a pointer. So another function of control spring is it provides controlling torque. Next we have pointer and scale also. The pointer should be of lightweight so that it can easily deflect with the help of deflecting torque, and there is a scale you can see here. So below the scale there is a mirror placed to avoid parallax error. Now let us see the working principle of PMMC instruments. So when current flows through the coil, so it will generate a magnetic field which is proportional to the current in case of an ammeter. So here we have seen that the important torques which are required in an indicating instrument are deflecting torque, controlling torque, and damping torque. Deflecting torque, here it is produced by the action of the current in the coil and the magnetic field. Next, controlling torque is provided by two phosphorus, bronze, flat, spiral coiled, spherical springs. Then, apart from this providing controlling torque, these springs they serve as a flexible connection to the coil conductors also. Then damping torque is produced by the aluminium former. So this prevents the oscillations of the coil. So here the type of damping is eddy current damping. Now let us see the expression for torque produced in a Pmmc instrument. So consider this is the coil, this is the radius of the coil, and this is the length of the coil. So when a current flows through one turn coil situated in a magnetic field, a force is exerted on each side of the coil. So this is according to Lorentz force equation. Force F is equal to BIL. It is given in newtons. So here B is the magnetic flux density in Tesla or Weber per meter square. I is the current in amperes and L is the length of the coil in meters. So we know that force is acting on each side of the coil. So there are two sides of the coil. So on each side of the coil, force is acting. So this side as well as this side. And this coil is made up of n number of turns. So there are n number of turns on the coil. So therefore, force equation we can write it as F is equal to, since two sides, 2 we have written BIL into N. Next, so therefore, the force on each side acts at a radius r, producing a deflecting torque. So deflecting torque TD is equal to F cross R you can write. So F is equal to 2 BI L into N into R. So this is equal to N into this 2R is equal to D from the diagram which I have shown in the previously. So this is equal to BIL into A. It is equal to BIN into A. This L into D will be equal to A. So therefore TD is equal to deflecting torque is equal to BIN into A. This is the magnetic flux density, this is the current, and this is the number of turns of the coil, and this is area of the coil. So the controlling torque is given by Kc into T theta. So controlling torque produced by the springs, we know that Tc is equal to E into B into T cube by 12 into L. So in this into theta. So we can write it as Tc is equal to some K into theta, where Kc is equal to E into B into T cube by 12 into L, where E is the Young's modulus, B is the breadth, T is the thickness, and L is the length. So Kc is a spring constant, we know, spring constant. At steady state position, controlling torque is equal to deflecting torque. So we can write Tc is equal to Td. So that is Kc into theta is equal to Bi N into A. From this expression, theta is equal to Bi N into A divided by Kc. So here B, N and A are constant, whereas I is variable. So we can write Tc is equal, theta is equal to K into I. So theta is proportional to I. That is, the pointer deflection is proportional to the coil current. So from this we can say that here the scale of PMMC instrument is linear. So for 1 milliampere current, if the meter produces 1 centimeter, there is deflection of 1 centimeter, then 2 milliamperes will produce 2 centimeter movement of the coil. Next, errors in PMMC instrument. So coming to the errors, there are three types of errors. First is weakening of permanent magnets due to aging. So we are using permanent magnets in PMMC instrument as we have seen there. So these permanent magnets, they lose their magnetism with after some point of time. So in order to reduce this, what we are doing is we are initially reducing its magnetism, and then whatever the magnetism is remaining, that is left forever. So how we are doing this is by using by heating and vibration treatment. by heating and vibration treatment. With this process will reduce some magnetism. So magnetism which will be left, so that will remain as it is. Next, weakening of springs due to aging and temperature effects. So spring is affected by aging and also temperature. So in order to reduce this, so springs, they are made up of phosphorus bronze, and to reduce the effect of temperature on the spring, so in order to reduce the effect of temperature on the spring, we use two spiral hair springs. Next, change in resistance of moving coil with temperature. So as we know that, the coil which is made up of copper, it has some resistance. So that resistance will change according to temperature, with temperature variations. In order to avoid that, what we do is we connect a small resistance called as swamping resistor. It is connected in series with the moving coil in order to avoid the effect of temperature variations. Next, let us see the advantages and disadvantages of PMMC instrument. So advantages are uniform scale for the instrument. So as we have seen that the scale is theta is proportional to I. So whatever current we need to measure, same amount of deflection will be there in the pointer. So theta is proportional to I. Power consumption is very low. So this is one of the important requirement of an instrument. Its power should consume very less power. A single instrument can be used for different current and voltage ranges. And another important advantage is torque to weight ratio is high. So because of this, it gives higher accuracy. So what is torque to weight ratio? So it is nothing but the ratio of torque to weight of an instrument. So this ratio should be very high. So in order to be high, the weight of the instrument should be reduced. So here weight of the instrument is nothing but the pointer which is there, or which deflects under the action of the deflecting force on the scale. It should have less weight, so that the torque which is produced should be higher than the weight of the pointer. So this torque to weight ratio, it indicates the performance of the system. Performance of the system is based upon torque to weight ratio. Another one is sensitivity of the instrument is also based on torque to weight ratio. So higher the torque to weight ratio, higher will be the performance, or the performance will be good, and higher will be the sensitivity of the instrument. Next, coming to the demerits of PMMC instrument. This instrument can be used for DC supply only. So we cannot use it for AC. So why? Because it measures, PMMC instrument measures the average of the PMMC instrument measures average value of the quantity being measured. In AC, we have positive half cycle and negative half cycle of the current. So during positive half cycle of the current, it will move in one direction. The pointer will move in one direction, and during negative half cycle, it has to move in the other direction. It will move in the other direction. So what it does is, so during negative half cycle, the pointer will move backwards. During negative half cycle, direction of current is reversed. So direction of torque will also reverse. So net torque which is experienced will be 0. Net torque is 0. So due to this, there will be no deflection on the scale. So hence the pointer will indicate 0. The cost of the instrument is more than MI instruments, moving iron instrument. The coil of PMMC instrument is small, light, and it can carry very small currents. Since the construction of an accurate instrument with a moving coil to carry current greater than 100 milliamperes is impractical owing to the bulk and weight of the coil which is required. So we know that in PMMC instrument, the springs carry the current. Springs which are used, two spiral springs are there. So these are used to carry the current. So with the help, the current is flowing here, and then so current enters into one coil and then it flows out from the other coil. So the current carrying capacity of the coil is limited. So it can carry, so without any adjustment, we can use PMMC instrument for measuring current up to 20 milliamperes by using shunts. So in order to increase the range of this PMMC instrument to be used as an ammeter, so the current greater than 20 milliamperes has to be bypassed. So this is done by connecting this meter in parallel with a resistance called as shunt resistance. So this can carry only 20 milliamperes. If we want to measure the current of 1 amperes, the remaining 1 minus 20 milliamperes will flow in the shunt resistance. So in this way, we can extend the range of PMMC instrument, which is to be used as an ammeter. Now let us see the range extension of an ammeter. So same diagram I have drawn here. So here we have, this is the meter, PMMC instrument. This is RMS, the resistance of the internal resistance of the meter. Then RSH is the shunt resistance. This is the shunt resistance which is connected in parallel with the PMMC meter. IM is the full scale deflection of the deflection current of the meter. ISH is shunt current in amperes, and I is the current which is to be measured. Now let us see the expression. So we can write ISH is equal to total current I minus IM. So this is the expression. We can write RSH is equal to IM into RM divided by ISH. So we know that V is equal to ISH into RSH. That is also equal to IM into RM. IM into RM. So from this we can write RSH is equal to IM RM by ISH. So IM RM by ISH. So in this we can substitute ISH as ISH is equal to I minus IM. So RSH is equal to RM divided by I minus divided by IM. So which is equal to, from this expression we can write RSH is equal to RM by M minus 1, where M is equal to I by IM. So here we can write it as RM by M minus 1. RSH is equal to M minus RM divided by M minus 1, where M is equal to I by IM. And again we can write M is equal to, so from this RSH is equal to RM by M minus 1. So from this we can write M minus 1 is equal to RM by RSH. So M is equal to 1 plus RM by RSH. So this is the formula, where M is called multiplying power of the shunt, and it is defined as the ratio of the total current to the current through the coil or the meter, you can say. So we can modify this ammeter in order to extend its range to different values. Suppose let M1, so we have connected here, this is the PMMC instrument, and this is the RM is the meter resistance, and suppose we need to measure 3 different currents. We need to extend its range to I1, I2, I3 and I4. So 4 different currents need to be measured. So in that case, what we have done is we have inserted shunt resistance R1, R2, R3 and R4 in parallel with Pmmc instrument, and there is a selector switch here connected, so which can connect any one of the resistance according to the requirement of the user. So this is a make before break switch. So we can write R1 here. So same formula we can apply. R1 is equal to Rm by M1 minus 1, where M1 is equal to I1 divided by Im, and R2 is equal to Rm by M2 minus 1, where M2 is equal to I2 by Im. So in this way, for 4 different currents, we have 4 different resistor values. Next, range extension of voltmeter. So generally a voltmeter, a PMMC voltmeter can measure up to 100 millivolts. In order to extend its range, we use a series multiplier. We use a series resistance called as multiplier connected in series with, so this is RSC, this one is the PMMC instrument. So this is meter resistance is Rm. We connect a series resistance called as multiplier in series with meter resistance Rm in order to extend its range to, so with this arrangement we can measure up to 20,000 to 30,000 volts. Series resistance is called as multiplier. The function of the multiplier is to limit the current through the basic meter so that the meter current does not exceed the full scale deflection. The value of the multiplier required to extend the voltage range is calculated from the diagram we can see. Im is the full scale deflection of the current. Rm is internal resistance of the meter. RSC is multiplier resistance. Vm is the voltage across the meter for the current I. V is the full range voltage of the instrument. From this we can write V is equal to, same current Im is flowing through this and this resistance. We can write Im into RSC plus Rm. So from this we know that Vm is equal to, voltage drop across the meter is given by Vm is equal to Im into Rm. So take the ratio of these two. V divided by Vm will be equal to Im into RSC plus Rm divided by Im into Rm. So these two will get cancelled. This is equal to RSC plus Rm divided by Rm. So this is V by Vm. So this is nothing but it is equal to, this is equal to M. So M can be written as, so M minus 1 is equal to RSC by Rm. So from this we can write RSC is equal to Rm into M minus 1. So with that, this is the series resistance which need to be inserted in order to extend the range of voltmeter. Here M is called as multiplying factor of the multiplier and it is given by M is equal to V by Vm. V is the full scale deflection voltage and Vm is the meter voltage. You can see voltage across the meter, Vm is voltage across the meter and V is full range voltage of the instrument. So this is another arrangement of the circuit by means of which we can extend the range of voltmeter. So it has been, so there are 4 different ranges. So if there are 4 different ranges are required, we need to insert 4 different resistor values, R1, R2, R3 and R4. So same formulas will apply. So addition of number of multiplier together with the range switch provides together with the workable ranges. A multi-range voltmeter using 4 position switch and 4 multipliers for the voltage range V1, V2, V3 and V4 are given. So multiplier resistance you can calculate by RSC is equal to Rm into M minus 1. So in this way.
Like, share and subscribe. Hit the bell icon for more updates.